Hi everyone, welcome to today's DaSSWeb, and it is our pleasure to welcome Bruno Veloso, who is our invited speaker today. Bruno is assistant professor at the FEB, Faculty of Economics, University of Porto, and senior researcher at Riyadh in Esctec. He develops scientific research in artificial intelligence, which involves multi-agent systems and machine learning. Bruno has authored more than 80 publications in peer-reviewed journals and book chapters and international proceedings. During the last few years, he has served in scientific committees of several international conferences and as associate editor of 2 journals. Okay, I'm sorry. I was just checking if the recording was on. So, okay. Bruno, thank you very much for accepting our invitation, and the floor is yours.
Okay, thank you so much, Eduarda. First of all, I want to give a thank you for the committee of DaSSWeb to invite me for this talk. Thank you, Eduarda and Paula, for this invitation. So today I will talk about one work that I collaborate in a project. This project is called Emeritus, and this project is related with crimes in environment. So the topic of our presentation is more enough is better. It means that we are trying to use a few shot learner to identify illegal landfill wastes in several countries. One of the cases is in Portugal, and we also use segmentation models. So we will start explaining our motivation. Then I will describe the challenges that we have during this project, the goals that we received from the project also. I will explain detailed the methodology, and finally we have the experiments and results that we obtained with our method, and finally the conclusions and future research lines. So we know that illegal landfills can have a huge social and economic impact. We can observe several news in the newspapers about environment crimes. I selected one of these news about the amount of money that is required to deal with waste crimes in UK. So according to the Environment Agency, it estimates that at least 900 million pounds per year are required to handle this illegal waste. So, but looking to the numbers on Europe, we can observe using the information about this trash out NGO that publish every year the results that in Europe we have a lot of illegal landfills. Some of them are more related with plastic landfills. Other types are like old or construction. So there are different types of illegal landfills that are spread by Europe. But if we look better to our Portuguese case, we see that we have the similar pattern. So it means that at least in Portugal, we have almost 300 different locations with different type of illegal waste like plastics, household construction materials, glass, metal, and so on. So these type of problems are very common. It will have impact not only on environment, like in the soil, on contamination of the water, air pollution, and so on. But we have some costs to clean up these illegal places. So we have also some main problems with the public health because some materials can expel toxic substances. So, and these places are typically located nearby vulnerable communities. So these are the four points that have more impact by the illegal landfills that we found on the literature. So there are some challenges that we have. The first one and the most important one is the data. Nowadays, we know that we have maybe 100 of different satellites collecting information from different types for images, infrared information, radar, but all this type of data is, or at least has some costs, and the access of public images are not so common. So there is a lot of scarce annotated data to work on segmentation, for example. And another issue that we found is that the images that are available, publicly available, are or don't have a good resolution. And when we don't have a good resolution, it's difficult to identify very small locations where it contains, for example, construction debris or construction materials that are put there illegally. Another point related with data is that we don't know information about illegal activities that are spread in some places or some locations. And in other cases, we have some sensitive information, typically locations nearby police stations, some information about the army. So there are some places that we cannot have access to images from satellites. The other point or the other set of challenges are related with modeling. We know that we have several satellites in space, but they are collecting the information in a very specific sample rate. In some cases, one picture per week or one picture every 15 days. So it's difficult for us to detect in almost near real time new constructions, for example, the creation of new illegal landfills, and that part is very important. The other part is that traditionally segmentation models are very data hungry. It means that we have a lot or we need to have a lot of data to train these segmentation models. Otherwise, we cannot have a good performance. And these models, if they consume a lot of data, they also consume a lot of time to train, and they are computational costly. So we need to think in other solutions. So the goals of this project is basically try to use some public data sets that have high resolution images, for example, for binary classification, and try to build a segmentation model. The images that we adopted are from this website, aerialwaste.org, that contains at least 10,000 labels. So it means that they will give us the locations of possible illegal landfills. And we have at least 150 segmentation masks, and these masks can be very useful to train a classifier like I will explain in a few slides. But the second point is that we need also to have a good notion of what will be our metric that we'll adopt to understand the segmentation quality. One example is that imagine that we have here this picture on the left side. We have here in the middle some potential illegal landfills. You can see on the right side the output segmentation and the ground truth. It means that on these red regions we have the illegal landfills, and that's a very small dot there. So it's difficult to use these kind of images because they don't have a good resolution. At least we need better quality to achieve the better results possible. But to understand what we did, I need to explain a little bit what kind of models we used. The first set of models are related with segmentation. And we have three different types. The first two are related with semantic segmentation. It means that each pixel is assigned to a specific class. And you can see here on this example where we can observe the different objects that are related with the same class, like the cube, have the same color. And we have the other option, which is the instance segmentation. The instance segmentation is somehow similar with the semantic one, but it means that, or the key difference is that for each object, it will belongs to a different instance. So it means that the cube not belongs to the same class, but we have different instances of the class cube. Finally, the third segmentation type of models are diagnostic ones. So they divided the images in different regions without knowing any information about the object. And we have this model developed by Meta. Is called segmentation editing model. And this SAM model generates outputs like this one, where we can see that every single object on the picture will be segmented, and we can select each object to classify with a different classifier afterwards. So the key differences are that the semantic and instance segmentation requires label data, and diagnostic is label free. So it means is a kind of non-supervised technique. But we need also to understand what is another point is class activation maps. The class activation maps can help us to identify the classification decision. Let me first show you one picture. The traditional classification maps or CAMs have this kind of aspect here, where we have the regions where it have higher probability of belong to a specific class. So these are the type of decision masks that CNN models, convolutional neural network models, generated. So typically they work in 3 steps. We train a classifier like a CNN, and our final convolution feature map can be basically a linear combination using the weights of the output layer. And that will generate the heat map that we saw on this picture here on the right side. The type of applications of these type of models are more related with weakly supervised object location. We can apply for segmentation proposals or try to interpret better what is happening in terms of classification. So on this slide, we can observe one example of applying a CNN on our input image. So this is typically the traditional image or the common image that we have for illegal landfill identification. And the CAM will try to generate probabilities of the regions where we have a positive label. In this case, the red region is more located with this small space there where we have some garbage. The other topic that we also need to have some knowledge is about the SAM model that we adopted in this work. The SAM, or Segment Anything model, is developed it was developed by Meta. It have the capability of segment every single object using only prompts. In this case, the prompts are a little bit different when compared with the prompts from ChatGPT. So basically what we gave to the model is the points or the bounding boxes or the full image that we want to segment. This model, it was trained with more than 1 billion masks. So we have a lot of data to train this SAM model. This is why we choose this module in our methodology. And because it is agnostic and we don't know the right labels on the real images that we have access, it's better to use a model like SAM to segment the places, the streets, the houses, and the illegal landfills, if it exists or not on the images. So our approach basically can be divided in 4 steps. So we have our input image that we observed on the previous slides. We can use a CNN model to generate the CAM, or the class activation map, to localize the waste. And based on this CAM mask, we can try to draw a bounding box. And with this bounding box, we can apply or prompt it to the SAM module and extract the segment. So basically, the most important part is that the CNN needs to work good. Otherwise, the bounding box will not be on the right place. And then we have some issues on the classification of the locations. So the next step after having segments and the CAM, or the classification activation map, we need to do some predictions. So basically, we filter the segments using the intersection between these CAM, or the classification activation maps, with the segments generated by the SAM model. And we have some segments are from a specific location. And then we have a classifier that tries to predict which segments belongs to the waste category or not. And this module basically contains, or this classifier on the right side contains few segments that we have available. And based on these segments, we can check if the data that is generated by the segmentation and the classification task can be a region of interest to be explored by the agency teams that will check if there is a illegal or not, or a normal place to put the garbage. So the output of the SAM module will be something like this. We have a lot of different colors, meaning all the objects that the model identified on the picture. We have the classification output based on the quantiles that I will explain in a few slides. We have the segments of interest. So basically it's the intersection of the classification output with the segmentation output. And finally, with these segments of interest, we can generate some predictions about what are the right places to check if there is an illegal landfill or not. So our classifier will check some visual features that we'll mention, like prototypes. And these features are basically the average values of the 3 channels that we have on the images, RGB. So we are trying to capture the color tone of each segment. We have also the histograms. So we try to capture the distribution across the color channels. And for each segment, we need to compare it with the list of segments that we have on the training set of our classifier. So we use distance-based metrics like Euclidean distances for example, for the average RGB channels, and the Kullback labeler divergence to measure the distances between histograms. So the goal here is try to capture the similarity or the visual similarity that we have in the segments. We know that this is a limitation because in some satellites we have only grayscale colors, or in other cases we have infrared information and other type of radar information. So, but we don't have access to this paid version of the images. So we need to work with only the open and public data. And on this case, we have only images. So our research goals is try to evaluate the segmentation using only a few set of annotations, are these prototypes that we have, and try to combine in some way the classification with diagnostic segmentation model. And then on the last step, try to predict the segment prototypes that have more interest to check and validate if they are correctly identified as illegal landfills. So there are a few small subsets of data sets available on the different websites. We have the air waste, which is the data set we adopted to work. We have also someone related with urban segmentation, SpaceNet about roads, buildings, and floods. But all these data sets contains a very few amount of labels to train the classifiers. And even in some cases, they don't have the segmentation masks to validate with our technique. So our experimental setup is follows this list. So basically, we have a data set containing almost 170 annotated high-resolution images of positive illegal landfills. So we split the data set in 70% for training and 30% for testing. So to ensure that we don't have overlap of images on the training and testing set. Our classification model, our CNN, we use the ResNet 50 to detect the presence of waste. For the segmentation model, we use the SAM agnostic mask generation model from Meta. And finally, we have some parameters that we tried, the quantiles, to define the threshold of the classification activation map. In our results, the best value for quantile is 0.94. We have also the epsilon threshold to control the similarity matching in the predictive segmentation. And we used a combined metric with the coverage, the false positive rate, and the DICE. The DICE basically measures the similarity between the masks and typically is used on imbalanced data sets. So our alphas, here alpha 1, alpha 2, and alpha 3, in our experiments, we used these values, 0.4, 0.3, and 0.3. So we have a weighted average of these three metrics here. And our results, starting by the CAM threshold, we can see that using different quantiles, the region of interest to derive the bounding box can be can be very different. So looking to these 5 pictures, the most interesting one is the 0.94 because the region of interest is almost overlapping the two illegal landfills that we have on the picture, but we run these to every single image that we have on the data set. And using this combined metric that combines the coverage, the false positive rate, and the dice, we can observe that, for example, when we are looking only for the average distance between the colors, the best epsilon for the decision boundary is 8. Using histograms, the values can be very different. So in our experiments, we observed that for the combined metric with epsilon equals to 1, we achieved the best results. So here there is one picture that we looking only to these two plots on the right side. We can see that increasing the quantiles, basically we are decreasing the coverage. If we increase the epsilon, so increase the size of decision boundary, we are increasing the coverage. So we need to have a balance between these two parameters. And if we look to the false positive rate, we have almost the same pattern. So it means that if we increase the quantile, we are decreasing the false positive rate, which is good. And if we increase the decision boundary, the epsilon, we can see that the false positive rate can also increase or decrease depending if we combine with quantiles. So for the histograms, we observed almost the same pattern. So we have a decrease of the coverage and a false positive rate if we increase the quantiles. And again, if we change the epsilon, we can also have a decrease of the coverage and the false positive rate. So the main results is that the coverage can increase with epsilon, but must need to have some trade-offs depending on the application that we need. So in some real use cases, like when we use this system to identify illegal landfills, it's good to have a very small false positive rate. Otherwise, the police teams in the field must need to check a lot of places. So we need to decrease this false positive rate as much as possible. But in other cases, we need to have better coverage. So we need to have a balance here depending on the application needs that we defined it. So in conclusions, or the main conclusions of this work, in terms of achievements, we have this proposal that is very good segment places where we can have possible illegal landfills. So the combination of the class activation maps working together with segment anything model, we can identify potential good places to check if they are illegal landfills or not. In terms of results, we need to have this coverage or good trade-off between the quantiles and the epsilon, because in some applications, we need to have a very small false positive rate. And for future work, we are focused on trying to see if we can concatenate histograms instead of having the average of all image channels. And we also want to explore different color spaces or color channels like infrared or different grayscale image. And finally, we want to also to learn the epsilon from the training dataset. And based on that, try to improve overall this system that is deployed to help, we hope, some environment agency specialists to identify the illegal landfills. So this project is developed under the support of this Emeritus project. which is a European project founded. You have here some contacts. Matthias is a postdoc student that worked at Liad, myself, and thank you if you have any questions about this topic. This work, it was presented in ECAI on the prestigious applications on artificial intelligence and won the best paper award. So this work is very important in terms of sustainability, environment, crimes, and so on. So thank you so much for your time. And I don't know if you have any questions about the model, the proposal, the results. I'm completely free now to answer your questions.